centers and the configurations around these chiral centers. So a chiral center is usually what makes a molecule chiral, or make it have handedness. It would make it have enantiomers. It was a non-superluminal image. See my earlier short video for more information on that. So a chiral center is any atom, generally carbon, that has 4 different substituents. What I mean 4 different is not that you have 2 methyl and then you have 2 hydrogen, or 1 ethyl and then 1 hydrogen and 2 hydrogen. No. All 4 are distinct. So you might have, say, the carbon here, say, make this a chiral center. It could have an oxygen going, hydroxyl going over here. It could have a methyl group going over here. It could have an ethyl group over here. And you know what? We'll just draw the hydrogen for giggles. So this would be a chiral center, but it's easier to see if I were to draw it like this. Where the wedge, which is this one, is going out of the page, and the dashes are going into the page. Right. So for about any chiral center, you have 2 different possible configurations. You have the R configuration and the S configuration. This will make sense in a second. So how you determine which configuration this is called the Cahn-Ingold, and then there's something else I can't remember off the top of my head. Give me a second. Cahn-Ingold-Prelog system. And this may come up later in your study. So you're going to give each of these substituents around the chiral center a priority for what is the highest. And so you look at the first atom that comes after the carbon, and then you see an oxygen, a carbon, and a hydrogen. So you're going to give that one with the highest atomic number, label 1, and the lowest, label 1, and the lowest atomic number, label 4. This will be 4. And then you're going to look at the second substitution. So for this carbon, you would have 3 hydrogens, and as compared to this one, you have a carbon and 2 hydrogens. So carbon is clearly higher than hydrogen, so this will get a higher number than this. Do you see how that works out? Now we're going to redraw the molecule so that the fourth group is behind the page, because it's not already behind the page. If it's already behind the page, good for you. We're going to redraw it so the fourth group is behind the page. So we're going to rotate everything this way. And in this particular example, then you end up getting hydrogen here, wedge oxygen here, and then you end up getting a methyl, and then you end up getting an ethyl. So remember the ordering from before. We have this is 1, 2, 3, and 4. So going 1, 2, 3, ignoring 4, going 1, 2, 3, the whole thing, the rotation from 1 to 3 is counterclockwise, which makes this the S enantiomer. And similarly, if this is clockwise, the other enantiomer, this would be the R enantiomer. So you put that in front of the IUPAC name. So for this molecule, that would be, this would be 1-hydroxy butane, but it would be R 2-hydroxybutane. Do you get that? And so you use this priority system when you get this, and then you can get to the configuration. Now the other special case is if you have a double bond. So let me draw a very similar molecule with a double bond. I'm going to make that group, and now we have a double bond to oxygen here, and we have a methyl group. So we're looking at this one right here. Now a double bond counts as 2 single bonds. So this would keep the numbering the same as before. And then so this would be 1, and this would be 2, because it counts as, sorry, I did it wrong. That would be 1, and that would be 2, because a double bond is considered the same as 2 single bonds. And then this would be 3, and this would be 4. I'm creeping. But this molecule is achiral because this is an sp3 hybridized sp2 hybridized carbon, as in it does not have 4 different substituents. Do you get that? It only has 3 different substituents. But if the double bond was in one of the substituents, at like so, then the double bond would count the same as 2 single bonds as well. And then you simply apply these rules. And that's about it. Thanks for listening, and